So, good
Okay.
morning, everyone. Thank you for the invitation. It's such an honor. Okay, so my talk is about computational ghost imaging, principles and applications. Again, I'm Ritz from the National Institute of Physics, UP Diliman. Okay, so when we think of the word imaging, let me start with this one. When we think of the word imaging, what we usually have in mind is smartphone cameras or compact system cameras, also known as mirrorless cameras or DSLRs, right? So when we try to remove uh, for example, the lens in here, what we'll directly see is the imaging sensor, which is the one that's converting electrical signal to optical signal. So it's usually made of a CCD chip or a CMOS chip, and that looks like this. So it has RGB components, and usually they have a range from 1 megapixel to 24 megapixels nowadays. So it's made of an array of detectors, and there's an electrical circuit that's embedded within it that's converting the light signal to an electrical one. So that's usually how it works. So when we say when a CCD chip, for example, has a resolution of 1 megapixel, that means 1 million single pixel detectors or 1 million photo detector units. And that's why they're usually expensive to build. Now, what if we take just a single unit, a single photo detector unit from these millions of photo detectors, and then we use this single pixel detector or this photo detector unit to image something? And how will that work when you only have one detector out of millions of detectors? Now, with this technique called computational ghost imaging, what it does is to pass on the two-dimensionality of the detector array to your light source through the use of a spatial light modulator, for example, which modulates the intensity of the light source or the phase. In this case, what we need is to modulate the intensity of the light source. To say you have a classical light source here, or even a quantum source, a laser source. So what you do is to pass on or to pass on this light source here to your spatial light modulator, and you modulate the light by producing several structured patterns, and you project this into your object. So for example, for this one, it's a transparency object, and you use a single pixel detector. In this case, it's a bucket detector, which collects all the transmitted light from this transparency, from the combination of this modulated light with that of the transparency object. And then from the correlations between this modulated light and the signal collected by the bucket detector, you'll be able to form uh, the image of this object. So a ghost image is actually an image that's retrieved using a computational ghost imaging or a single pixel imaging system. So it only needs a single pixel detector and a modulated light source. So those are the only two things that you need. Instead of having millions of detectors, you only need one. But then again, you need your light source to be modulated in terms of intensity in this case. Okay, so for a computational ghost imaging, for a formal definition, it produces images using a bucket detector instead of an array of 2D sensors, and it uses a spatial light modulator to generate programmable illumination patterns onto the target scene. So it has several advantages actually over the conventional imaging, which uses detector arrays. So one is that it's adaptive in most environments. Number two, it has a flexible light path configuration. You can have a reflective um, type SLM, for example, to image a reflective type object instead of a transmissive one. It's capable also of non-line of sight imaging. So the bucket detector or the single pixel detector just collects all the light, reflected light from the target scene. And so it does not need to, or the single pixel detector rather actually does not have to face the target scene itself. Unlike with conventional imaging, wherein the imaging sensor and the lens actually has to be in line with that of the target object. And it can also have high signal to noise ratio, well, depending on the algorithm, the computational imaging algorithm that you're going to use. But the disadvantage of this one over the conventional imaging, which uses detector arrays, is that it has a very long computational time, since it only uses a single pixel detector. But again, you can have several image retrieval algorithms, for example, compressive sensing, to reduce this computational time. And most of the time, it's still expensive because of the use of SLM. But actually, you can build one which is very cheap depending on the components that you're going to use. So for building a single pixel camera, we can actually build a low cost one. Okay, um, for the stages, so the first one is you build the LOX meter or the intensity meter first, and then you can proceed on to sensor characterization. Just like with any imaging system, you need to do this. And then you also need to calibrate the entire system, entire imaging system once you've collected the components and combined them to form the setup. So for the first stage in building your single pixel camera, you need to have a LOX meter. So for this one, the components are, of course, a single pixel detector. You can have a light dependent resistor, an LDR, which is very cheap actually, and it only costs around 10 Philippine peso. It's widely available. It's sensitive to light intensity changes, and yeah, and again, it's very cheap. And the other component that you need to build the LOX meter is the analog to digital converter. You can use an Arduino board, for example, uh, to convert the optical signal collected by the LDR onto an electrical signal. So it has analog pins, as you can see here, and then it also has an input voltage. Usually it's constant at 5 volts, and then of course the ground. And then you need to have a resistor to usually impede current flow. So um, after collecting these components, you can build your LOX meter prototype that looks like this. With an LDR, you can make a very simple voltage divider circuit, and this is already proportional actually to your intensity signal. So this one here, in the LOX meter prototype, what I have here is just the LDR and the resistor connected in series to form the voltage divider uh, circuit. All right. Now, for the second stage, of course, you need to characterize the sensor or calibrate the sensor itself. In this case, with this one here, the boxed area is the uh, LOX meter system or the voltage divider system. The its output voltage is connected to a data acquisition system, say an oscilloscope, and then you have a light source here, which is an LED connected also to a resistor. And then you feed a square wave, for example. So for this part here, what we want to show or what we want to do is to see or to compare the input signal coming uh, from the square waves or from the function generator, and then compare that with the output that's detected by your light dependent resistor. So again, this one is a square wave. Now, because LDRs have a slow response, what we expect to see is not a square wave, but a modulated square wave actually. So this is a setup for sensor characterizations. You have your input and output. We want to compare the two. Uh, this is the input square wave, the one in black. And as you can see here, the red plot is the output detected by the LDR. Again, it's slow. It takes time to reach a saturation signal or a constant signal. But from there, you can actually extract the time constant. In this case, it's around 25 milliseconds for the LDR that we use in our experiments. The time constant, or the time it takes to reach a saturation value or a constant value, is at 25 milliseconds, which is kind of slow, but it's already good. Yeah. So after obtaining this time constant, you already know the time delay between the projection and the capturing based on the time constant actually of the LDR. So the next step is to do system calibration, wherein you project increasing gray levels on a wide screen, and then you obtain the voltage reading. So as you can see here, LDRs have a nonlinear response. So this is a voltage as a function of gray level, which is proportional to intensity level. And this plot tells us that it's best to image at low light levels, because it's this region is the most linear, and therefore it's the most sensitive. And this can also be an advantage, because even if you have a dark environment, the LDR is still able to capture the signal with a relatively high signal to noise ratio. So again, this is the LDR's voltage response to changing light levels. So after you've built the LOX meter, you've characterized the sensor, you've calibrated the entire imaging system, you can now build your experimental setup. So in our case, our spatial light modulator is just a commercial projector. And then the ADC here is again the Arduino board. The single pixel detector here is just an LDR, which is very cheap. And then we employ a particular technique called Fourier ghost imaging, wherein we project sinusoidal patterns, series of sinusoidal patterns onto the object. And for each pattern, light signal is collected by your single pixel detector, and then the signal gets converted. The analog signal collected by by the single pixel detector is converted to a digital signal using your Arduino board. And from the correlations of the illumination pattern, or of the structured patterns, and the collected signal by this LDR here, you can combine all of these signals to retrieve the image of the scene here. Um, just a brief explanation about Fourier ghost imaging. So it just uses the knowledge of Fourier transform, and utilizes knowledge that most of the information of natural images are located in low spatial frequency bands. For example, here, these are standard images being used for image processing. This is the Fourier transform, the 2D Fourier transform of these images. As you can see, the power spectrum is concentrated on the low frequencies. Okay, so this is a Fourier spectrum. So this tells us that it's sufficient to actually image the low frequencies, and then from there we'll be able to see most of the details already of the object. So what you do again is to project sinusoidal patterns, and from there extract the reflectivity, the total reflectivity of the object from the combined um, uh, signals from structured patterns. So for the results, so here's a sample test object, the UP1, and from the calibrated imaging system, computational ghost imaging system, which is a very low-cost one with the use of LDR and a commercial projector. This is the sample result that we have obtained for a 1% Fourier spectrum, and then 10% Fourier spectrum. By taking the inverse Fourier transform of this one, we were able to see or reconstruct the image of UP here. So at 1%, you can already see the details of UP, and even at 10%, um, we can see a clearer image of UP, although it's kind of noisy because of the absence of a focusing lens. But to increase the signal to noise ratio, you can actually place uh, collecting lens or a focusing lens in front of the single pixel detector to at least increase or to reduce the noise signal and increase the SNR the system. So here, the lensless FGI system is capable of sub-Nyquist sampling. The results have been published actually just last year in American Journal of Physics. So my co-authors here are Doctors Nathaniel Hermosa and Maricor Soriano. So to summarize that part, we were able to we propose and demonstrate a method for lowering the cost of computational ghost imaging setups by employing cheaper devices such as commercial projector and a light dependent resistor. The proposed imaging system produces good reconstructions of uh, the test object even at 10% spectral coverage, which is well below sub-Nyquist sampling. For the other part of my talk, it's just a simple extension actually of the 2D ghost imaging. So if you add a few more resistors, you can do 3D ghost imaging or 3D computational ghost imaging. So we have this technique called photometric stereo wherein you have multiple light sources, for example, and then just a single camera capturing light reflected by a sample seen from each of these light sources. So for a modified version of this photometric stereo system, what you can have is that you invoke Helmholtz reciprocity, which tells you that a light ray and its reverse ray undergo a match optical adventure. So at the location of the light sources, you can place your cameras, and then at the location of the camera, you can place your light source, and then we can use our single pixel detector system to retrieve actually uh, a 3D the 3D structure of the scene from the shading information collected by the shading information collected by each single pixel detector. So the camera here is a single pixel detector. All right. So for the mathematical formulation for that one, so first what you want to do is to define the albedo scaled surface normal. So let me just go back here. So the surface normal vector is this one, for example, for this particular point on the surface, and you want to record this one for all the points on the sample scene or on your target scene. Okay, so the normal vectors will actually give you later on the 3D shape of the object. Um, after representing the albedo scale surface normal, what you can do is to extract the intensity or collect the intensity and recast that collected by all detectors and recast that into a matrix form that looks like this. We solve for this um, variable here using matrix inversion, linearly squares algorithm. And then we have this formula here for solving GJ. And then from there, the surface normal and sub J can be extracted. And this one here is what you need to extract the 3D shape of the object. Using this algorithm called semi-calibrated photometric stereo, if the light magnitude is unknown, for example, that's hitting the single pixel detectors, but the positions of the detectors are known, we can invoke a minimization technique to extract or to optimize the lighting parameters here. We can reduce that or we can further employ a nonlinear least squares approach called the Levenberg-Marquardt algorithm to optimize the lighting parameters. After optimizing, we can then solve for the surface elevation from the extracted surface normal earlier, and then from there just use a line integral to extract the 3D shape of the object. Another method which we do to lower the signal to noise ratio to increase rather the signal to noise ratio and the to the images first before employing the SCPS or semi-calibrated photometric series algorithm is to apodize the 2D images, which means to remove the foot, or mathematically it's remove or smoothen sharp discontinuity in a mathematical function. So here we use a Gaussian filter. We multiply it to the noisy spectrum. Um, it has this form here. It's a 2D Gaussian function. The sigma here is the standard deviation of the Gaussian distribution. And then you can play with this value before multiplying it um, with the 2D Fourier spectrum, with the 2D Fourier spectrum collected by the single pixel detectors. So for the experiment, of course, what you do first is to calibrate the detectors and the entire imaging system. You obtain the Fourier spectra using the 3D imaging system. We apodize each spectrum to minimize noise artifacts, and then we apply the semi-calibrated photometric stereo technique, which optimizes the lighting parameters from the images themselves, and then we display 3D. Here we compared four techniques. The direct photometric stereo, is an uncalibrated system. It just assumes that the light magnitude collected by each detector is the same. For the one with the plus A, it employs the apodization technique, which is a multiplication of the Gaussian filter for noise reductions. All in all, there are four cases. So this is the built experimental setup for 3D computational ghost imaging. We have 6 LDRs here. You only need at least three. You only need actually at least three, yeah, to collect signals from a sample scene. Um, for the calibration part, so as you can see here, these are the calibration curves collected by our system for the 6 single pixel detectors. So even if they were manufactured in the same way, as you can see, there are still discrepancies, which means that they have differing sensitivities, and which tells us that the light collected by the LDRs may not, the light magnitude collected by the LDRs may not be the same. And so we can use the semi-calibrated photometric serial algorithm to solve this problem of differing sensitivities. For the objects, these are simple ones. We just wanted to show or to build up to show rather a proof of concept actually for this 3D CGI. We have here a hemisphere, a cone-shaped object, and a 3D sine wave object. Okay. Um, so for the results of the apodization, so each detector is actually obtains the spectrum first. We apodize the Fourier spectrum, which shows us that after apodizing, we can actually minimize the noise collected by the detectors. Um, and then after that, as here is a sample effect of apodization on the noisy images. So starting with um, a standard deviation for the Gaussian function of equivalent to 1 up to zero point 0.1. So here, as you can see, as sigma reduces again, okay, we as sigma reduces here, the radius of the Gaussian mask, of course, reduces as well, and we see that the reconstructed image by the LDR has now better or higher signal to noise ratio. So we're essentially cleaning the image before feeding it to the photometric stereo algorithm. So as you can see here, for the cone object, we were able to clean it with the apodization technique as well as with the sine object. And upon combining and then applying the photometric stereo technique, let me skip this one. These are sample 3D images for the four cases. So with the direct case, the images are tilted because of the differing sensitivities of the LDRs. Um, and then there are corrugation artifacts because of the noise. But upon application of the apodization technique, as you can see, we were able to clean them. And then applying the semi-calibrated photometric stereo, we were able to remove this tilt due to differing sensitivities and exposures. And then finally, with the semi-calibrated photometric stereo algorithm plus the combined with apodization, we were able to create accurate 3D images of the cone, the hemisphere, and the sine wave object. So here is a sample 3D view of the object, rotated 3D view of the cone object. So as you can see here, the best one again is the combination of the semi-calibrated case plus the apodized cases with the following percent errors. So for the semi-calibrated case without apodization, it's kind of high because of the noise artifacts. But if we apodize them or if we clean them before feeding it to the algorithm, we were able to obtain a low percent error of 6.86%. Okay. So uh, we can also evaluate the intensity error maps obtained by the system by evaluating this or by evaluating G, the albedo scaled surface normal estimated using the photometric stereo algorithm. As we can see here, again, the semi-calibrated plus apodized case gives the best results. So this is actually a plot of the root mean square error across all the images captured by all detectors for each case and then for each object. So the lower the values, the better, right? So finally, to summarize, we achieved 3D computational ghost imaging with multiple photoresistors serving as single pixel detectors using semi-calibrated lighting approach plus apodization technique. The system does not need special calibration objects or additional optical components to perform accurate 3D imaging, making it cheap and adaptable. And of course, it can also be used or for applications outside the visible spectrum. So that's all for my talk. Thank you for listening.
All right. Salamat, Rich.
Okay.
So, if you have, for the audience, if you have questions, you can type in your questions at the chat box and Q&A box. Okay, so any questions from the panel? So, maybe I can start. Uh, the output of the computational processing is a complex field, right?
Yes, sir. Yes, sir. Complex.
Complex, right?
Uh-uh.
So what could be the interpretation or the significance of the phase of the complex field?
We haven't looked into that yet. Actually, the face part. Before, I tried actually extracting the face and use that to uh, extract the 3D shape from the object using this technique called Fourier transform profilometry. Like it's like an analogy, but the 3D shape that was extracted using the face that was captured by the system was kind of noisy. It was not good. It has lots of discontinuities, and so I'm not sure what I was doing wrong. But I can look into that further. Actually, the face part that was
Yeah.
captured. So for now,
Uh,
I'm focusing on the on the real part. Yeah, the magnitude.
Actually, the noisy distribution is expected, di ba? Kasi it's a optically rough object. So
Yes, yes.
maybe we'll have some uh, meaningful, significant uh, signal if maybe you do some comparison of phases. So like an initial state and then final state, you do the phase subtraction. Maybe it will reveal correlation between the phases. So just maybe something to try.
Yeah.
All right.
But actually, uh, the main source of error for this one, actually, as you can see, it has a very noisy background. It's probably the absence of a collecting lens or a focusing lens in front of the single pixel detector. But uh, if we try to use one, probably we can reduce the noise collected by this one. The
Yeah,
noise.
but that is the amplitude, right?
Yes, sir.
That's
This
the amplitude.
is attitude part.
All right. So nobody's raising their hands. Maybe I'll
Sir,
ask another one. See,
Sir
Vani.
Vanny Valois. Hi,
Vani.
I'm Vanny Valois from Riken, and thank you for your very nice presentation. I actually have a few questions, but maybe for now I'll just limit it to two. The my questions are mostly related to resolution. So
Mm-hmm.
you showed that in your method you have a projector, and then you put a sinusoidal, I would say, film, which will act as your SLM. And does this regulate the resolution of your system, the resolution in terms of the smallest feature that can be resolved in your structure? So right now
Yeah.
you just used two large UP, but if you made the UP even smaller, can you still resolve the U and P using the same sinusoidal pattern, or do you have to increase the frequency of the
Yes.
sinusoidal
Yes.
pattern? Okay.
Yeah. Okay. So for the first question, actually, for your question, I'm not really using sinusoidal films. So these are
Mhm.
patterns generated by a computer, and then you feed it to your projector,
Yes.
and then the scene gets illuminated by this structured light pattern,
Mm-hmm.
which has the shape of a sinusoidal, which is a 2D sinusoidal shape. Okay,
Yes.
so for your ghost imaging algorithm, what it does actually is to what you do is you project series of sinusoidal patterns of varying frequencies
Okay.
from low to high. So of
Mm-hmm.
course, if you only use sinusoidal frequencies with low sinusoidal patterns with low frequencies,
Mm-hmm.
what you're able to obtain in the Fourier spectrum are the low frequency details, which
Yes.
translates to the general details of the object, but not the smooth transition from, say, from black to white, which is a high frequency. Okay.
Yes.
So if you want to get the higher frequency signals, what you
Mm-hmm.
do is you use sinusoidal patterns of higher frequencies. And if
Yes.
you want to retrieve
Mm-hmm.
smaller details, yeah, then you need to project um, all the sinusoidal patterns with frequency starting from low to high. And that actually depends on the size of the smallest detail in your test object.
And so the more sinusoidal projections you use, does it mean higher computation time, or it
Yes,
doesn't?
yes.
Yeah.
High or longer
Yes.
acquisition time, actually
Longer acquisition time. Mm.
longer acquisition time.
And actually, one more question is also related to resolution, but it's for your apodization factor for the three-dimensional Fourier ghost imaging. So you mentioned that, and you also showed very nicely that when you apply the apodization factor, the images become smoothened out. But have
Yes.
you ever tried using a sample wherein right now you're only using very smooth surfaces, but if you introduce some like fine features or some color like black spots, can the apodization factor also retrieve that information, or will it treat it just like some kind of noise and smoothen everything out, and then you can't see
Uh,
it anymore?
I haven't tried that yet, but
Mm-hmm.
usually before applying a optimization technique, we first convert an RGB image to a grayscale one.
Yes.
In terms of the signals, actually, so the optimization technique, it's essentially a low pass filter,
Mm-hmm.
so or yeah, a low pass filter. So it's only as you can see here with the image of the cone or of
Mm.
the hemisphere. Okay, as you decrease the size of the Gaussian mask, the image gets blurry. So
Yes.
you're essentially removing um, the details with the uh, or the details here in the spatial image
Mm-hmm.
with the higher resolution. So it may not be that uh, good to apply for images with smaller details, but you can actually play with the value of sigma, so as not to smoothen out the details that you need, the details that you want for the 2D image.
All right.
Okay, thank you.
Okay, maybe I have the last question. Can you describe an application where ghost imaging is particularly useful, a practical application where this kind of technique will be able to can be used?
Yes, sir. Actually, I wasn't able to put them here, but it has actually been used for several applications outside the visible spectrum, such as, for example, there's this there's this group which did single pixel imaging of or computational ghost imaging of methane gas, so for detection of leakage, so using a very low cost single pixel imaging system. It has also been applied for ghost spectroscopy, digital ghost holography even, sir, and non-line of sight imaging. So the cool thing here is that the single pixel detector, as I mentioned earlier, it does not have to face the object itself or the target object itself. Um, it can be facing away from the object and still able to capture the signal or the structures of the signal if you have a reflective type object in front of it.
All
So,
right. So final. Why the phrase ghost imaging?
ghost
Why is it
imaging,
called ghost?
uh, ghost imaging because you're using light that hasn't really physically initially interacted with the object. The computational ghost imaging actually started with quantum ghost imaging or quantum entanglement experiments, and the ghost imaging part was actually derived from that. It's imaging using light that has never physically interacted with the object. Right. Or in this case, for the computational ghost imaging, the single pixel detector does not really have a resolution. You don't have an eye. You're like imaging without a camera. And any image captured by a computational ghost imaging is called a ghost image. You're imaging without 2D, the conventional digital camera that we know of. But instead,
All right.
you're just imaging using a single pixel camera. Yeah.
All right. So with that, thank you, Rich, for your presentation. So
Uh,
let's now proceed to the
Thank
next presenter. All right.